For years, the phrase 1.5 degrees Celsius has been treated by the public like a flexible political target. We hear it mentioned in climate summits and assume it just means wearing a slightly thinner jacket in December or turning up the air conditioning a bit sooner in the summer. But that number is a hard physical boundary. It represents the strict maximum limit of Earth's climate stability. To understand why, we have to stop looking at global average temperatures on a thermometer and instead zoom in on specific, localized geographic systems to see what happens when their physical limits are breached. Crossing 1.5 degrees initiates a cascade of physical, chemical, and biological failures in the systems that keep our environment stable. Let's start with the mechanical failures, specifically at the poles. Greenland's ice sheet acts as Earth's air conditioner, and its structure is breaking down. As the atmosphere warms, the surface of the ice melts, forming massive lakes of slush and water right on top of the glacier. That water doesn't just sit there. It drains downward through deep vertical shafts called moulins. When millions of gallons of water reach the bedrock below, it acts as a high-pressure lubricant, causing the entire ice sheet to slide faster into the ocean. Down in Antarctica, the mechanics are different. Here, massive land glaciers are held back by floating tongues of ice called ice shelves. They act like a physical plug, a giant cork blocking the ice behind them from flowing out to sea. But warmer ocean currents are eroding those shelves from underneath. When that cork eventually thins out and collapses, the inland glaciers behind it surge forward into the water. These are continent-sized frozen dams, holding back enough water to raise global sea levels by several meters. Once those structural dams break, we lock in a multi-century trajectory of rising oceans. The crisis moves from the remote poles directly onto our shorelines. Depending on our emissions, seas are projected to rise anywhere from half a meter to a full meter by 2100. For low-lying metropolises like Jakarta, Miami, or Bangkok, that means permanent, unfixable inundation. But we tend to picture sea level rise like water overflowing a bathtub. The reality is far more insidious. It is slow, relentless, and highly chemical. As the ocean creeps higher, the heavy, dense saltwater pushes inland beneath the surface. It forces its way into coastal freshwater aquifers and saturates the soil. We call this saltwater intrusion. This is catastrophic for global agricultural hubs like the Nile and Mekong deltas. Salt acts as a poison to traditional crops like rice and wheat. Unable to survive the high salinity, lush farmlands and coastal forests undergo extreme vegetation dieback, transforming into unproductive, barren salt marshes. The ocean doesn't even need to wash over the streets to do its damage. This invisible chemical invasion turns a rising tide into a global food security crisis. While the coasts deal with water and salt, the equatorial regions face a direct threat to human biology, driven by something called wet bulb temperature. Our bodies maintain a safe internal temperature through a very specific mechanism. We sweat, and the surrounding air evaporates that sweat, cooling the skin. Wet bulb temperature measures heat and humidity combined. If that measurement reaches 35 degrees Celsius, about 95 degrees Fahrenheit, the air is completely saturated. It is physically impossible for sweat to evaporate. If global temperatures push past 1.5 degrees, vast stretches of the Amazon basin, Southeast Asia, and parts of Africa will frequently cross this unsurvivable threshold. Hitting that biological limit means outdoor labor simply stops. You cannot farm, and you cannot build. It guarantees mass mortality and forces millions of people to migrate away from the equator just to survive. Look at the map of the year 2100 if we breach that line. We are looking at drowned coastal megacities, massive agricultural failures in our major deltas, and unsurvivable heat zones dividing the globe. The most severe danger lies in how these systems begin to accelerate one another, tripping into self-reinforcing cycles known as tipping points. A tipping point is a self-reinforcing cycle. For example, as the Earth warms, the frozen ground in the Arctic, the permafrost, begins to thaw, splitting open and releasing massive reserves of trapped methane. That methane causes even more warming, which melts even more permafrost. That is the ultimate consequence of blowing past 1.5 degrees. Humanity loses its agency. We transfer the controls of the climate from our own carbon emissions directly to the Earth's natural momentum. We turn a problem we could have stopped into a runaway train we can no longer break.